I'm back working on the NCR vintage computer, and if you saw the previous video, you know that we're having an issue with the floppy drive interface. It won't read or boot from the floppy disk. Now, the main repairs I have to do with these machines, I've got two of these. I've got a black and white one, which is the one we're looking at now. I've got a colour one as well. Now, the floppy interface, I'm told, works on the colour version. The reason I prefer to try and carry out the repairs on the hard drive interfaces using the black and white machine is because it's a much simpler arrangement to work on. It's not as cumbersome. The boards, the interface board is smaller. The colour version is really just a 3-channel version of this board, the daughter board that plugs into the top of the main CPU board. But it's much easier working with this arrangement than the colour one, so I would prefer to use this for working on the hard drive interfaces. As you can see, I've got all the boards laid out on the bench now. It is actually now powered up. I've got the usual message on the screen, and I've made these extenders just so I can move the daughter board off to one side and still run the machine. That will make it far easier to try and work on this. It's doing exactly the same thing in the, laid out like this as it was with the board plugged in directly. Now, before I made these extenders, I was just probing around the boards, just getting a general feel for how the machine's behaving. And unfortunately, I think this machine has far more issues than just not booting from floppy disk. I think a lot of the devices on this are starting to fail. I actually had a machine a few months ago that was in a similar condition. In fact, it was in far worse cosmetic state, but it had a similar issue where a lot of the ICs were failing. And it does seem to be becoming more common as time goes on. These vintage machines, the devices are aging and they're starting to underperform. Now, this arrangement is relatively complicated because it's a Z80, or this particular machine has the Z80 processor. You can put a different processor on the other side of the main board if you want. This has got the Z80, and it uses a DMA controller for transferring data, and it's a 4-channel DMA. For anyone that's interested, it's an 8237 and 4-channel, and one of the channels is used for sending data to the display. Another channel is used for the floppy drive controller. And I believe there's some contention on the board and they're fighting over use of the DMA. Unfortunately, I don't have the schematic for this particular version of the machine. I've got the schematic for the colour, but it's a very different layout and a different circuit, so I can't really use that. If anyone out there has the schematic for the black and white version of this, I would appreciate a copy. But at the moment I'm just having to kind of look at the colour schematic and try and translate that into this arrangement, but unfortunately the main differences in the circuitry seem to be in the DMA control circuits, so that's really where I need to be looking. But unfortunately we're going to have to kind of muddle our way through this because the schematic is different in that respect. Now, this is doing kind of a strange thing. If I boot up the machine with the drive door closed, and incidentally someone did point out that you shouldn't really do that. It's absolutely correct. You shouldn't power up machines with the floppy disk door closed. Now, in this case it's a sacrificial disk. I've done this before, so I kind of know what I'm doing, but there is danger, especially on some of the drives that don't have the head load solenoid. That is the ones where closing the drive door lowers the head onto the media. Now, this doesn't. These drives have a head load solenoid, and that's controlled through software. So although you can see that the heads go down when I close the door, they're not going all the way down. There's a solenoid here that takes them the rest of the way down, so the heads are not actually in contact with the media when you power it up anyway. But even so, it's good practice to have the door open when you power up the machine. Now, as I was saying, this machine behaves differently. If I have the door closed, in fact I'll demonstrate it. If I close the drive door, so the drive door is now closed, I'll power off the machine. We'll have our probe on standby, and what we'll look at is pin 25 of the Z80. and that is the bus request pin. So I'll power the machine off, and when we power it back on, if you keep a close eye on the scope, so I'll power it on now. Notice that we're getting some activity on the bus request, and if I press the enter key it should try to boot again. So notice that we're getting activity on the bus request, and that's coming from the floppy drive controller. If I look at pin 23 on the Z80, that's the bus acknowledge pin, and I press the enter key again, notice that we're getting bus acknowledge. So the Z80 is kind of granting the floppy drive controller access to the bus. What I'll do now is I'll open the drive door and we'll reboot the machine again. I'll go back to pin 25, power up the machine, we'll wait for it to finish booting up. Okay, so nothing so far. If I close the drive door, you hear the head load solenoid engaged there, still nothing. I've got the message on the screen saying that we should basically press the enter key. So I'll press the enter key, you'll hear the head load solenoid re-engage, but if you keep an eye on the scope, there is nothing at all. And the machine has basically crashed, you can't do anything with it now at all. If I press the enter key again, we're not getting anything. So the machine's essentially crashed, and the only way now to proceed is to recycle it. So we'll turn it off, turn it back on. So what appears to be happening is it seems to be starting the process of trying to read a floppy drive controller, and then for whatever reason it's just hanging. And when we start probing around, the reason for that does quickly become fairly apparent. If we start probing around on these, we've got a couple of shift registers up here that are responsible for sending data to the display. If we look at the signal on one of those, it doesn't look too bad. What I'm going to do now is close the drive door and recycle the machine just so it doesn't keep hanging. We'll wait until it boots up. Now, as I said, the display and the floppy drive share the DMA controller. So if we go back to this pin, you can see there's some activity on there. But if I press the enter key to try and boot from floppy, if you keep an eye on the scope, you'll notice that the signal levels are very low. Some are down to 1.5 volts. So I suspect there's some contention there. What I'll do now is power the machine off with the drive door open, leave the drive door open, power it back on. We'll close the drive door. Now what we're seeing on the scope at the moment is the data being sent through to the video displays. There's a message on the screen, that's what we're seeing. If you watch the Z80 series, Designing the Z80 Computer, this is the same sort of video output that we saw in those videos. But this is coming through a DMA channel. If I now press the enter key, I'll close the drive door now. Remember, we booted it up with the drive door open. I've closed the drive door. I'll now press the enter key, but keep a careful eye on the scope. Notice we got a brief flurry of very poor looking signals, and then the machine crashed, and now there's nothing there at all. Even the data we had initially has gone, and all we're getting on the screen now is the cursor. We no longer get the video display, and the machine is now dead. It won't do anything, it's crashed. So I suspect what's happening is that it's trying to boot up, to recycle it again. I suspect what it's doing is trying to start up. It's not getting as far as reading the disk. It's as soon as it tries to go into DMA mode, the entire machine hangs. So I suspect that some of the glue logic around the DMA controller is not working. I've tried a replacement DMA controller, didn't make any difference. So I suspect some of the glue logic that's driving this is not doing what it's supposed to, possibly just the age of the devices. But as I said, unfortunately I don't have a schematic, so it's going to be a bit of a difficult one to try and resolve. Where I'm going to start is I'm going to attach the logic analyzer to the floppy drive controller, and all I'm going to do there is just see if the data coming out of it is what we expect. So we'll just hook up the logic analyzer go through a few read cycles for the floppy drive, see if it is capable of reading the data from the floppy disk. We'll see if that matches what we believe is on the disk itself, and if that's coming out of the floppy drive controller the way it should, then we'll know that the floppy drive interface is basically working, and the next thing we'll do is attach the logic analyzer to the DMA controller. Now if you're working on machines and you need to hook up the logic analyzer to the floppy drive controller, do not use one of these. If you attach this to the floppy drive controller chip, you'll stop it working. Some of the pins on the floppy drive controller are for things like the voltage controlled oscillator, and if you attach something like this, you'll change the frequency at which that's working, and you'll stop the drive working anyway, so you won't be able to use it. So don't use these on floppy drive controller devices. Instead, just select the pins you want and use these little grabber hooks, and as long as you steer clear of the sensitive pins, you're not going to stop the interface from working. So I'll get this hooked up, we'll look at the logic analyzer, we'll try booting up again and see if there's any data coming out of the floppy drive device at all in both of our modes. That's where we have the door closed when we power up, and when we close the door after power up and the system hangs. It's kind of odd that it's behaving differently in the two modes. If it's a DMA interface issue, you'd kind of think it'd do the same thing in both modes where you close the door after power up, but like I said, I think it's the glue logic that's controlling this, and it's obviously behaving differently depending on how we start the machine up. So I'll get the analyzer attached and we'll see what we get. Okay, it's the next day and I've spent quite a bit of time working on this now. I've been going through trying to figure out what's going on with it, and it appears to have quite a few different faults, and they're not all related to the floppy drive controller. I think there are other issues with this particular machine. So what I've been doing so far is I found that the floppy drive controller wasn't doing what it's supposed to. You can see I've got it hooked up to the logic analyzer. I'll show you the logic analyzer screen in a few minutes. But what I was finding, if you're familiar with the floppy drive controllers, then they're relatively simple devices, but you need to send them certain commands to tell them which track, which sector, and what to do when they find the correct data. And what I found was that the commands that were being seen by the floppy drive controller chip were just nonsense. None of them were proper commands, and the way the commands are loaded is there's an address line going into the device that allows you to select either the status or the data register, and then depending on whether you're reading or writing, then the device will let you read the status register or write to the data register or read from the data register. So if you're sending data to the device, you write it into the data register, and if you're reading from the device, of course you read it from the data register. But the way that this system works, it uses DMA. Now if you're not familiar with DMA, if you go and look at my recent videos on the Z80 project, I explain in a bit of detail there how DMA works. The difference here is there is a dedicated DMA controller device. Quite a complex device, but the way the system works, I mean, this is kind of the short version, it's a bit more complex than this, but you program the floppy drive controller with the parameters that you want to use, and you then start it running. Once it's got a byte from the floppy disk, it should generate a request to the Z80 asking it if it can use the address bus data bus. Now because it's using a DMA controller, it actually sends that request to the DMA controller. It's a 4-channel DMA controller, so it sends that request to one of the 4 channels. The DMA controller then effectively asks the Z80 for permission to use the data address buses and control lines, and once that is granted through the bus acknowledge mechanism on the Z80, the DMA controller then goes through it's a relatively complex cycle, and it's made a bit more complex because it needs to supply a 16-bit address. Now if you recall with the Z80 project, that 16-bit address was provided by a 16-bit counter. But this device only has 8 bits or 8 bits of address output. So they're the low order bits for the address that's going to be used for the transfer. And the second or the upper 8 bits are provided through a multiplexed data bus. So the 8-bit data that comes into the device, those pins are also used to output the 8 bits of address, the high 8 bits of address. Those 8 bits are latched into a latch, and then the lower 8 bits and the upper 8 bits from the latch are used as the 16-bit address, and then it moves on to the next phase of the transfer. And it does that twice. It does once for a read, in this case from our device, and then once for a write to RAM. And all this has to be choreographed with some glue logic, and I believe it's in the glue logic that we have the issue. I have tried a replacement DMA just to eliminate it, but the data actually does seem to be getting through to the RAM. However, when I first started investigating this, because the commands that the floppy drive controller was receiving were just garbage, it wasn't really doing anything. It was just outputting nonsense data. In fact, it was outputting the same 3 bytes each time. I think it was 20, 04 and 01, and that's all it would output. It wouldn't send any sensible data. Now unfortunately I don't have the schematic for this particular machine. I have one for the color machine we'll look at in some future videos, but it is very different. The layout looks fairly similar, but all the designations for the ICs are different, so it's very difficult trying to trace this type of fault, because it's quite a complex fault and I have no way to check from A to B, because I don't know what's supposed to be connected to what. So I'm just going through trying to reverse engineer the circuit. So I didn't video the first stage because it involved physically trying to trace tracks through to see where they went and which devices were responsible for the various parts of the overall operation of the system. And I had to keep turning the board over, and as you can imagine, that's not easy with the camera in the way. So I'm working around the camera all the time, of course, when you're looking at this. And what I found was there was a broken via. So just off to the left, what's now covered over with these grabbers, there's a broken via. The vias are these little through board connections you can see dotted around, and one was broken, so there wasn't a connection from the top layer to the bottom layer, and that was preventing the correct data getting through to the in fact the right data was getting there, it just wasn't being seen at the right time. So if we looked further back through the logic analyzer trace, I could see the correct data values were being sent, but they weren't in line with the chip enable and the write signals going to the device, and that was down to an issue with the glue logic because of the broken via. So I corrected that, and we now appear to be getting the correct data coming out of the floppy disk. So I'll just move the camera, we'll have a quick look at the logic analyzer and I'll show you what we're getting. So I have printed off the relevant page. There is a manual that shows the listing for the CPM BIOS, and we should be getting the first few bytes. In fact, we should be getting all the bytes, of course, but if we just look on the logic analyzer for the first few bytes, we should be able to see what we're actually reading from the disk. I've done a blow up of this section. This is the first part of that code. I've done a blow up of this so you can see hopefully what we should be getting. So it starts off at address 0, and we should be getting C3 2100 43 etc. Now there will be an offset here, so where it's saying C3 2100, we'll actually be getting C3 2120, and this is a jump over this text. It's a jump to here, and this code is equivalent to the second stage bootloader that I showed for the Z80 project. So the first stage bootloader will be in the ROM. I don't have a listing for that, but the second stage bootloader is this. This is what's in the user manual, and it's obviously part of CPM. And so we've got this bootloader. The first instruction is a jump to the actual code, which is here, and where it says 0021, the compiler will have had an offset, and the offset will be 2000 hex, so it will read C32120, because these are obviously reversed the way the Z80 works. And the reason, and that will give you an address here of 2021 hex, and the reason there's an offset for this code is because the ROM occupies the lower 2000 hex bytes, and so this bootloader is loaded into RAM above the ROM. It obviously can't share the same part of the address, otherwise the system won't run. So this is the first thing we should see coming off the disk. It's the second stage bootloader, so I'll move the camera and we'll read the floppy disk and see what's actually coming off it. We won't get this the first time because at the moment I just have a test disk in here, and it's just formatted using the Z80 project. And if you recall, the data value for that is fixed for all the bytes, and we'll see those bytes appearing when we look at the logic analyzer, assuming the disk is being read correctly. So I'll move the camera and we'll see what we're getting. So looking at the logic analyzer screen, I will arm the analyzer, and I'm now going to press the return key on the keyboard. We've got the analyzer set to trigger on DRQ, so that's the output from the floppy drive controller that goes high when it thinks there's a byte to be read, or if it needs a byte to be written to it. In this case, we should be reading bytes from it. So I'll press the key on the keyboard. You hear the drive, and we've got some data. So when I scroll through this, and what we're looking for now is a read. That's the read is active low, so a low read of the data register. This A0 line is the A0 line on the floppy drive controller chip, and when we're reading the data register, that will be high. So what we're looking for is the blue line to go low and the white line to go high, and that's the data value that we should then be seeing. So if we start scrolling through, and we've got one here, so we've got a low value on the read line, high on the A0, and if we look at the data value, it's E5. And that might sound familiar for anyone that's been watching the Z80 series, so we'll keep scrolling through. And after a shot, these other reads, by the way, it's reading the status register, which is why the A0 line is low. That's the status register, and when it's high, it's the data register. So we'll keep going through looking for another read with the A0 line high. We've got one here, E5 again. Now these E5 values are of course the format values that I write to the floppy disk in the Z80 project when I'm writing data. So what I'm going to do now, because this seems to be working, I'm going to put an actual boot disk for this, what we believe is a boot disk for this machine. I'm actually not so sure now. I'm starting to think this might just be an incompatibility of the boot disk. So I'll put the boot disk in that I've got. Try not to knock the camera. Close the drive door, and we'll now do another read. So I'll arm the logic analyzer, press the enter key. Okay, so we've got our first read, and the first value is C3, and if we look at our data sheet, then we should be getting C3 for that value. The next value should be 21, so we'll keep scrolling across. And this is the next one, and the value is indeed 21. So the next one, now this is where it will vary because we're on the actual machine, so there will be an offset here to the top of the ROM. So we'll scroll across till we'll see the next read. Okay, so we're there, and as you can see, the value is 20. So it's showing as 0 on here. Like I said, there'll be an offset, and that's the upper byte for the address. So the address is 2021, so that's what we were expecting. The next value should be 43. Which is here, and as you can see, the value is indeed 43. We'll keep going across. The next one should be 50. it is indeed 50. We'll do one more and the next one should be 4D. And it is indeed 4D. So as you can see, the correct values are now coming out of the floppy drive controller. So I'll move the camera back down. So what I've done is trace all this through, and the data is getting as far as the DMA controller. We're getting the right control signals being generated, and the data actually seems to be making it through to the RAM. So my thoughts at this point are either we've got some weird glue logic issue and it's a timing problem, but the timing does seem to be correct, or it's just simply the wrong boot disk and the system is not seeing it correctly. Unfortunately, I haven't found the listing yet for the source code for the ROM, so I don't really want to spend the time reverse engineering that. If you've seen some of my previous videos when I've done that on other machines, basically you can decompile it and then start stepping through to find out exactly what the system is doing, trying to load the CPM code and bootloader. But as I say, I don't really want to do that. It's very time consuming. It's not my machine, so I'm not sure I'm willing to go to the trouble of spending 30 or 40 hours reverse engineering the ROM. One other thing that's odd, and why I believe there are other faults, is if we try to start the machine with the drive door open. So turn the machine off, drive doors open, turn the machine on, let it finish booting up. Okay, I'll put the disk in, close the drive door. Now if you recall that the clunk is the head load solenoid. Well, if we now press the enter key, then it does something completely different. And if we look at the logic analyzer, I won't show it to you because there's nothing to see, it does not read any data. So it's kind of strange that it should still be in its boot up state. Now it does differentiate between cold boots and warm boots, but I don't think that's the issue here. Now what I can do is force a reset. I don't recommend doing this, but the circuit arrangement for reset on this is fairly safe to do this if we do it fairly quickly. I'm going to force a reset by forcing the reset pin of the Z80 low. So I'm going to do that now. If you listen to the drive, okay, so if you force a reset, it does successfully read the disk even if the door was closed after the machine was booted up. So it is something to do with the boot up process, of course, but again, without the source code for the ROM, it'd be quite difficult trying to figure out exactly why it's doing that. I'm not sure how much further I'm going to go with this machine. I think it's got various faults, and without being confident I've got the right boot disk, and this, if it's the wrong boot disk, and all this is a complete waste of time apart from getting the floppy drive controller working in the first place. There are other faults. If we look at some of the devices, they are running extremely hot. Some of the devices on the display board, I don't know if you can see this, are running, it's hard to get this lined up, they're running over 70 degrees. I managed to get it on there, can't quite get it lined up. But they're running extremely hot, and if you get this properly lined up, they're showing about 72 degrees. This has been on for about 20 minutes, and they just keep getting hotter and hotter. They're too hot to put your finger on now, and the standard TTL devices should not, of course, run that hot. The rest of the system seems fine. These devices down here look hot, but they're just the large-scale devices that do tend to run warm, but even so, they're only running at about 35 or 40 degrees. But the ones in the back, as I say, are running over 70, and that, of course, is not correct. So there's something weird going on back there. So what I'm probably going to do for the next few videos, I might come back to this in the future if I can unearth any more information or a schematic, or get a source code listing for the ROM. I might come back and investigate this further. But really the reason for getting the floppy drive working was so that we can look at the main repair, which is the hard disk interface boards. And of course this machine, even if we get it working, I'm not sure it's going to be reliable enough to properly test the other hardware boards, so it might be as well now to switch over to the colour machine. It is a bit more cumbersome to use. The display board is bigger, it will get in the way when we're trying to do this, but it's better of course to have a working machine. If anyone out there has information on this machine, and in particular a listing for the ROM source code, it would be very interesting to see. And also, as you can see, there's a huge amount of rework on the display board, so I don't know what all that's about. There were different variants of this machine, of course, as with all vintage computers. They were really work in progress all the way through their lives, but quite an interesting machine to work on. Hopefully we'll get back to it, but if not, then hopefully the colour machine will be a bit more interesting and we'll have a bit more success with it.